Riboflavin, Wikipedia article audio. Riboflavin, also known as vitamin B2, is a vitamin found in food and used as a dietary supplement. As a supplement, it is used to prevent and treat riboflavin deficiency and prevent migraines. It may be given by mouth or injection. It is nearly always well tolerated. Normal doses are safe during pregnancy. Riboflavin is in the vitamin B group. It is required by the body for cellular respiration. Food sources include eggs, green vegetables, milk, and meat. Medical uses. Side effects. Riboflavin was discovered in 1920, isolated in 1933, and first made in 1935. It is on the World Health Organization's list of essential medicines, the most effective and safe medicines needed in a health system. Riboflavin is available as a generic medication and over-the-counter. In the United States, a month of supplements costs less than $25. Some countries require its addition to grains. Corneal ectasia is a progressive thinning of the cornea. The most common form of this condition is keratoconus. Collagen cross-linking by applying riboflavin topically then shining UV light is a method to slow progression of corneal ectasia by strengthening corneal tissue. As of 2017, a system is marketed by Terumo in Europe that is used to remove pathogens from blood. Donated blood is treated with riboflavin and then with ultraviolet light. In humans, there is no evidence for riboflavin toxicity produced by excessive intakes, in part because it has lower water solubility than other B vitamins, because absorption becomes less efficient as doses increase, and because what exceeds the absorption is excreted via the kidneys into urine. Even when 400 mg of riboflavin per day was given orally to subjects in one study for 3 months to investigate the efficacy of riboflavin in the prevention of migraine headache, no short-term side effects were reported. Although toxic doses can be administered by injection, any excess at nutritionally relevant doses is excreted in the urine, imparting a bright yellow color when in large quantities. Riboflavin functions as a coenzyme, meaning that it is required for enzymes to perform normal physiological actions. Specifically, the active forms of riboflavin, flavin mononucleotide and flavin adenine dinucleotide, function as cofactors for a variety of flavoprotein enzyme reactions. Function. For the molecular mechanism of action, see main articles flavin mononucleotide and flavin adenine dinucleotide. Food and beverages that provide riboflavin without fortification are milk, cheese, eggs, leaf vegetables, liver, kidneys, legumes, mushrooms, and almonds. Nutrition. The milling of cereals results in considerable loss of vitamin B2, so white flour is enriched in some countries such as US by addition of the vitamin. The enrichment of bread and ready-to-eat breakfast cereals contributes significantly to the dietary supply of vitamin B2. Polished rice is not usually enriched, because the vitamin's yellow color would make the rice visually unacceptable to the major rice consumption populations. However, most of the flavin content of whole brown rice is retained if the rice is steamed prior to milling. This process drives the flavins in the germ and alurone layers into the endosperm. Free riboflavin is naturally present in foods along with protein-bound FMN and FAD. Bovine milk contains mainly free riboflavin, with a minor contribution from FMN and FAD. In whole milk, 14% of the flavins are bound non-covalently to specific proteins. Egg white and egg yolk contain specialized riboflavin-binding proteins, which are required for storage of free riboflavin in the egg for use by the developing embryo. Riboflavin is added to baby foods, breakfast cereals, pastas, and vitamin-enriched meal replacement products. It is difficult to incorporate riboflavin into liquid products because it has poor solubility in water, hence the requirement for riboflavin 5-phosphate, a more soluble form of riboflavin. Riboflavin is also used as a food coloring and as such is designated in Europe as the E number E101. The U.S. Institute of Medicine updated estimated average requirements and recommended dietary allowances for riboflavin in 1998. The current EARs for riboflavin for women and men ages 14 and up are 0.9 mg/day and 1.1 mg/day, respectively. The RDAs are 1.1 and 1.3 mg/day, respectively. RDAs are higher than EARs so as to identify amounts that will cover people with higher than average requirements. RDA for pregnancy is 1.4 mg/day. RDA for lactation is 1.6 mg/day. For infants up to 12 months the adequate intake is 0.3 to 0.4 mg/day. And for children ages 1-13 years the RDA increases with age from 0.5 to 0.9 mg/day. As for safety, the IOM sets tolerable upper intake levels for vitamins and minerals when evidence is sufficient. In the case of riboflavin there is no OL, as there is no human data for adverse effects from high doses. Collectively the EARs, RDAs, ACE, and OLs are referred to as dietary reference intakes. Food sources. The European Food Safety Authority refers to the collective set of information as dietary reference values, with population reference intake instead of RDA, and average requirement instead of EAR. AI and OL defined the same as in United States. For women and men ages 15 and older the PRI is set at 1.6 mg/day. PRI for pregnancy is 1.9 mg/day, for lactation 2.0 mg/day. For children ages 1-14 years the pre-increase with age from 0.6 to 1.4 mg/day. These pre are higher than the US RDAs. The EFSA also reviewed the safety question and like the US, decided that there was not sufficient information to set as OL. Dietary recommendations. For U.S. food and dietary supplement labeling purposes the amount in a serving is expressed as a % of daily value. For riboflavin labeling purposes 100% of the daily value was 1.7 mg, but as of May 27, 2016 it was revised to 1.3 mg to bring it into agreement with the RDA. A table of the old and new adult daily values is provided at reference daily intake. The original deadline to be in compliance was July 28, 2018, but on September 29, 2017 the FDA released a proposed rule that extended the deadline to January 1, 2020 for large companies and January 1, 2021 for small companies. Deficiency. Mild deficiencies can exceed 50% of the population in third world countries and in refugee situations. Deficiency is uncommon in the United States and in other countries that have wheat flour, bread, pasta, cornmeal, or rice enrichment regulations. In the U.S., starting in the 1940s, flour, cornmeal, and rice have been fortified with B vitamins as a means of restoring some of what is lost in milling, bleaching and other processing. For adults 20 and older, average intake from food and beverages is 1.8 mg/day for women and 2.5 mg/day for men. An estimated 23% consume a riboflavin-containing dietary supplement that provides on average 10 mg. The U.S. Department of Health and Human Services conducts National Health and Nutrition Examination Survey every 2 years and reports food results in a series of reports referred to as What We Eat in America. From NHANES 2011-2012, estimates were that 8% of women and 3% of men consumed less than the RDA. When compared to the lower estimated average requirements, fewer than 3% did not achieve the EAR level. Anyone choosing a gluten-free or low-gluten diet should, however, as a precaution take a multivitamin/mineral dietary supplement which provides 100% DV for riboflavin and other B vitamins. Riboflavin deficiency results in stomatitis including painful red tongue with sore throat, chapped and fissured lips, and inflammation of the corners of the mouth. There can be oily scaly skin rashes on the scrotum, vulva, philtrum of the lip, or the nasolabial folds. The eyes can become itchy, watery, bloodshot, and sensitive to light. Due to interference with iron absorption, even mild to moderate riboflavin deficiency results in an anemia with normal cell size and normal hemoglobin content. This is distinct from anemia caused by deficiency of folic acid or cyanocobalamin, which causes anemia with large blood cells. Deficiency of riboflavin during pregnancy can result in birth defects including congenital heart defects and limb deformities. Signs and symptoms. The stomatitis symptoms are similar to those seen in pellagra, which is caused by niacin deficiency. Therefore, riboflavin deficiency is sometimes called pellagra sign pellagra, because it causes stomatitis but not widespread peripheral skin lesions characteristic of niacin deficiency. Riboflavin deficiency prolongs recovery from malaria, despite preventing growth of Plasmodium. In other animals, riboflavin deficiency results in lack of growth, failure to thrive, and eventual death. Experimental riboflavin deficiency in dogs results in growth failure, weakness, ataxia, and inability to stand. The animals collapse, become comatose, and die. During the deficiency state, dermatitis develops together with hair loss. Other signs include corneal opacity, lenticular cataracts, hemorrhagic adrenals, fatty degeneration of the kidney and liver, and inflammation of the mucous membrane of the gastrointestinal tract. Post-mortem studies in rhesus monkeys fed a riboflavin-deficient diet revealed about 1/3 the normal amount of riboflavin was present in the liver, which is the main storage organ for riboflavin in mammals. Riboflavin deficiency in birds results in low egg hatch rates. Overt clinical signs are rarely seen among inhabitants of the developed countries. The assessment of riboflavin status is essential for confirming cases with unspecific symptoms where deficiency is suspected. Riboflavin is continuously excreted in the urine of healthy individuals, making deficiency relatively common when dietary intake is insufficient. Riboflavin deficiency is usually found together with other nutrient deficiencies, particularly of other water-soluble vitamins. A deficiency of riboflavin can be primary, poor vitamin sources in one's daily diet, or secondary, which may be a result of conditions that affect absorption in the intestine, the body not being able to use the vitamin, or an increase in the excretion of the vitamin from the body. Subclinical deficiency has also been observed in women taking oral contraceptives, in the elderly, in people with eating disorders, chronic alcoholism, and in diseases such as HIV, inflammatory bowel disease, diabetes, and chronic heart disease. The Celiac Disease Foundation points out that a gluten-free diet may be low in riboflavin, as enriched wheat flour and wheat foods is a major dietary contribution to total riboflavin intake. Phototherapy to treat jaundice in infants can cause increased degradation of riboflavin, leading to deficiency if not monitored closely. Humans. Treatment involves a diet which includes an adequate amount of riboflavin-containing foods. Multivitamin and mineral dietary supplements often contain 100% of the daily value for riboflavin, and can be used by persons concerned about an inadequate diet. Over-the-counter dietary supplements are available in the United States with doses as high as 100 mg. But there is no evidence that these high doses have any additional benefit for healthy people. Other animals. As a chemical compound, riboflavin is a yellow-orange solid substance with poor solubility in water compared to other B vitamins. Visually, it imparts color to vitamin supplements. Flavoproteins of electron transport chain, including FMN in complex I and FAD in complex II. FAD is required for the production of pyridoxic acid from pyridoxal bipyridoxine 5-phosphate oxidase. The primary coenzyme form of vitamin B6 is FMN dependent. Oxidation of pyruvate, alpha-ketoglutarate, and branched-chain amino acids requires FAD in the shared E3 portion of their respective dehydrogenase complexes. Fatty acyl CoA dehydrogenase requires FAD in fatty acid oxidation. FAD is required to convert retinol to retinoic acid via cytosolic retinol dehydrogenase. Synthesis of an active form of folate from 5,10-methylene tetrahydrofolate by methylene tetrahydrofolate reductase is FADH2 dependent. FAD is required to convert tryptophan to niacin. Reduction of the oxidized form of glutathione to its reduced form by glutathione reductase is FAD dependent. Because riboflavin is fluorescent under UV light, dilute solutions are often used to detect leaks or to demonstrate coverage in an industrial system such as a chemical blend tank or bioreactor. Various biotechnological processes have been developed for industrial-scale riboflavin biosynthesis using different microorganisms, including filamentous fungi such as Ashbia gossypii, Candida famata, and Candida flavari, as well as the bacteria Corynebacterium ammoniagens and Bacillus subtilis. The latter organism has been genetically modified to both increase the bacteria's production of riboflavin and to introduce an antibiotic resistance marker, and is now successfully employed at a commercial scale to produce riboflavin for feed and food fortification purposes. The chemical company BASF has installed a plant in South Korea, which is specialized on riboflavin production using Ashbia gossypii. The concentrations of riboflavin in their modified strain are so high, that the mycelium has a reddish/brownish color and accumulates riboflavin crystals in the vacuoles, which will eventually burst the mycelium. Riboflavin is sometimes overproduced, possibly as a protective mechanism, by certain bacteria in the presence of high concentrations of hydrocarbons or aromatic compounds. One such organism is Micrococcus luteus, which develops a yellow color due to production of riboflavin while growing on pyridine, but not when grown on other substrates, such as succinic acid. Glutathione reductase is an nicotinamide adenine dinucleotide phosphate and FAD-dependent enzyme, and the major flavoprotein in erythrocyte. The measurement of the activity coefficient of erythrocyte glutathione reductase is the preferred method for assessing riboflavin status. It provides a measure of tissue saturation and long-term riboflavin status. In vitro enzyme activity in terms of activity coefficients is determined both with and without the addition of Fad to the medium. ACS represent a ratio of the enzyme's activity with Fad to the enzyme's activity without Fad. An AC of 1.2 to 1.4, riboflavin status is considered low when Fad is added to stimulate enzyme activity. An AC 1.4 suggests riboflavin deficiency. On the other hand, if Fad is added and AC is 1.2, then riboflavin status is considered acceptable. Tillotson and Basher reported that a decrease in the intakes of riboflavin was associated with increase in EGRAC. In the UK study of Norwich elderly, initial EGRAC values for both males and females were significantly correlated with those measured 2 years later, suggesting that EGRAC may be a reliable measure of long-term biochemical riboflavin status of individuals. These findings are consistent with earlier studies. Experimental balance studies indicate that urinary riboflavin excretion rates increase slowly with increasing intakes, until intake level approach 1.0 mg/d, when tissue saturation occurs. At higher intakes, the rate of excretion increases dramatically. Once intakes of 2.5 mg/d are reached, excretion becomes approximately equal to the rate of absorption. At such high intake, a significant proportion of the riboflavin intake is not absorbed. If urinary riboflavin excretion is 40 g per day are indicative of deficiency. Vitamin B was originally considered to have two components, a heat-labile vitamin B1 and a heat-stable vitamin B2. In the 1920s, vitamin B2 was thought to be the factor necessary for preventing pellagra. In 1923, Paul Georgi in Heidelberg was investigating egg white injury in rats. The curative factor for this condition was called vitamin H. Since both pellagra and vitamin H deficiency were associated with dermatitis, Georgi decided to test the effect of vitamin B2 on vitamin H deficiency in rats. He enlisted the service of Wagner Joreg in Kuhn's laboratory. In 1933, Kuhn, Georgi, and Wagner found that thiamine-free extracts of yeast, liver, or rice bran prevented the growth failure of rats fed a thiamine-supplemented diet. Diagnosis, causes, treatment, chemistry. Further, the researchers noted that a yellow-green fluorescence in each extract promoted rat growth, and that the intensity of fluorescence was proportional to the effect on growth. This observation enabled them to develop a rapid chemical and bioassay to isolate the factor from egg white in 1933, they called it ovoflavin. The same group then isolated the same preparation from whey using the same procedure. In 1934, Kuhn's group identified the structure of so-called flavin and synthesized vitamin B2. The name riboflavin comes from ribose and flavin, the ring moiety which imparts the yellow color to the oxidized molecule. The reduced form, which occurs in metabolism along with the oxidized form, is colorless. A 2017 review found that riboflavin may be useful to prevent migraines in adults, but found that clinical trials in adolescents and children had produced mixed outcomes. Industrial uses. Industrial synthesis. History. Name. Research.